Okay, so we're good to go. All right, so this is the help session on significant figures. This is an actual lesson. I will be covering this again as if we were doing this for the very first time. For those of you who have had very little with this or you don't remember it, we're just going to start from the very beginning and try to make it all the way through. I got a picture right here of a train that actually ran through the depot. Apparently the depot is on a hill. The train came in and on the tracks, overshot itself, and landed in the street below. This is actually the cover on a book called Scientific Error Analysis. Okay, obviously somebody made a mistake here. And what we want to talk about here is when we measure, we actually have a certain degree of estimate or uncertainty in our data. And every measurement that we make in science has an estimate built into it. It is unlike the math class where every number is what it is. A 5 in a math class is a 5. Here it's a 5 because somebody thought it was a 5 when they measured something. And there's always an embedded estimate or uncertainty. So it's about 5, and we need to figure out how close to 5 is it really. All right? Since there's an estimate embedded in, an estimate is a guess. That means it's uncertain, and that means uncertainty is actually embedded in part and is a part of every measurement. Okay, so how do you figure out how certain a number is? That's what today's discussion is about. Most measuring devices have markings by which the measurement is read. And these devices have a limit to the smallest quantity that they can measure. If you're trying to measure with a measuring cup, the smallest marking that you can measure is whatever's marked on there. You can't measure any finer than that. That's the smallest you can get. So the smallest quantity can be found by determining the value of that tiniest little marking on the device. Okay? Then you need to realize that once you've found the tiniest little marking and how much it measures, you are supposed to be able to estimate between the markings. All right, now it's important for you to have that skill because you're going to measure with all kinds of measuring devices in this class, and you have to figure out how big that marking is, and then that you can actually estimate how far it is between the markings. Here's an example. Here's a nail. If you want to know how long that nail is, you line the beginning up with a 0 here, and then you try to figure out where it ends. And so you zoom in on it like this, and you find out that the finest marking here is a tenth of whatever this is. These are centimeters, so tenths of a centimeter, right? And that finest marking then is a tenth of a centimeter. And you're supposed to be able to estimate then between the markings. So in this inset, you can see that the nail actually lands between the third and fourth markings. And that means that an estimate needs to be made between the third and fourth markings. Now you might say that seems to me to be halfway in between the two, and that's fine, but you said that seems to me, and as soon as you said that, you made a guess. You made an estimate. You built uncertainty into your measurement. It's fine, but you have to recognize that you did that. Okay? In this measurement, you know for sure that it passed the 6, so that's not a guess. You know for sure that it passed that little third marking, so that's not a guess. So you haven't made a guess until you got to the next digit, which was the 5. So the 5 is the estimated digit, and that involves uncertainty. Do you agree? Okay. These 3 reported digits, they all convey useful information. And for that reason, they're all called significant digits. Okay, they were significant. You actually interacted with the device, and you came up with those numbers. Some of them you were certain about, and the last one you weren't. Okay. How certain can you be that that last number was a 5? Well, you said you estimated it, right? You guessed. All right, well, how certain can you be that your guess is right? And how can you communicate to the next person that that's really a guess? That was an estimate. It was kind of a shot in the dark. How can you tell the next person who reads your measurement how precise that last measurement, that last digit really is? In general, your estimate should also come with a statement of possible error. Now here's how we do that. The limitations of any measuring device are usually reported as 1/2 of the smallest or finest marking that it has. In other words, when you get a person together with a device, the best they can usually do is about 1/2 of the finest marking. So, you put it all together. This ruler's smallest marking is 1 millimeter, or it's 1/10 of 1 centimeter. Okay? So now I'm going to put this whole thing together. The standard error for this ruler is give or take, plus or minus, could be more, could be less, 1/2 of the smallest division. Okay? Now, if you're reporting to someone else, then the measured value of the length of that nail should be reported as the certain values that you measured, the estimate that you put on the end, and the uncertainty, all put together. It looks like this. I'm sure of the 6, I'm sure of the 3, I guess the 5. Give or take about that much. Does that make sense? That's the whole package put together. You can do this with any device. You measure what you know for certain, you guess between the finest markings, and then you report your uncertainty as 1/2 of the finest marking. That's the way it's done with a ruler, with a thermometer, with anything we use in here, with a protractor for that matter. Okay, anything that has markings. Now, let's go back to that. Then the significant figures in any measurement include all of the digits that you know for certain and one last digit that you guessed. And we said both of them are significant. Even the estimate was significant. So now I come to a key concept here. Measurements that you make have to always be reported to the right number of significant figures. Because when you use your measurements, calculated answers that come out of them often depend on the number of significant figures that were in the original values to make the calculation. Let's put it this way. If you sort of know how much money he has and how much money she has, you put them together, how much money do you have together? And how precisely can you know it? Well, you would add what he has to what she has, right? But since you only sort of know what he has and sort of know what she has, then you sort of know what the two of you have, right? But you can't act like all of a sudden, just because you added those two quantities together, that you know now to a very high degree of precision how much money the two of you have. Do you understand? In other words, when you do math with estimates, the estimates transfer into the answer. So you got to watch the way you report the answer. And that's called the rules for significant figures. Okay, so here's how we do it. First of all, I want to take this little ruler very quickly, and I just want to look at some of these letters and see if I can figure out, this is a ruler, these are markings, the finest markings, these are tenths of centimeters or millimeters. And I'm going to just look and see, like an H, can I figure out what I would report for that? So I would say, well, it's beyond the 12, but it hasn't reached the 13 yet. So I know it's for sure between 12 and 13. That's not a guess. I can see that. I can also see that it's beyond the finest marking here, and it hasn't reached that marking there yet. So I know for sure that this is 12.9 something, and I haven't guessed yet. And I keep doing this until I have to guess. But now I have to guess. Somewhere between the 9 and the 10 here, these tiny little markings, I have to guess how far I think it is between here and here. And now it's my turn to guess. I don't know, maybe I would say that's a 6, and you might challenge me on that. You might say, well, I don't know, I think it's a 7 or a 5, okay? So that's my estimate. So what do I read to you? This is my measurement. 12.96, and my uncertainty or estimate or error would say, give or take, 1/2 of the finest marking, which is 1/10 of a centimeter. All right, put that all together, and I would say 12.96 plus or minus 0.05 centimeters. See how that works with a ruler then? Now you should be able to do that for each one of these. There are a couple of tricky ones. What if it lands exactly on one of the lines? And here's where it's real important. If you can go out to 2 decimals for this measurement, then you should be able to go out to 2 decimals for any measurement on this ruler, even if it lands on a line. That way you communicate the precision of the device and the uncertainty of the measurement. And if you chop it off, you are giving the impression that you measured this with a ruler that was marked in a different way, that didn't have the precision that this ruler has. Consequently, this one right here, the A that seems to land right on that line, should be reported as 12.5. As best I can tell, it's right on the 12.5, but I need an extra digit. What do you think I should put in? a 0. But that 0 had a meaning, right? It's not insignificant. You put it there for a purpose. So we're going to see here in just a moment that when you tag that 0 onto the end, you're trying to tell us, no, I didn't guess between 12 and 13 and just sort of thought it was about halfway. I think it's right spot on the line, and there's a line for me to confirm it on. So what are we going to do with this one? That seems to be right here on the 12. 12.00. You're going to add 2 zeros. In other words, you're going to make sure you still have 2 decimal places. Okay? You can always catch yourself making a mistake if you actually get more than one measurement off of the same device and they have different decimals. You're making a mistake. They should all have the same number of decimals. Okay? So that's how to read off of the ruler and make sure that you read it off with the right number of significant figures. Now, what if we do this backwards? What if, say, Chase brings to me the work that he just did on his lab, and I'm looking at the numbers that he wrote down. I'm not measuring them. I'm reading his numbers. Okay? So if you're reading a measurement that somebody else did, how do you know how many significant figures that number has? Okay? And it really comes down to this. It's all about the zeros. Because if it's not a 0, it's significant. So the question is, well, when is a 0 significant? Okay? Well, if you're not a 0, you're significant. That was rule number 1 right here. So if you look at a number like 673 and they're asking you how many significant figures it has, well, it has 3 of them. 1, 2, 3, all of those count. It doesn't matter if it has a decimal in it, 2.8, 2 significant figures. Now, what about zeros that are in between numbers that you've already found out are significant? We call that the sandwich rule. If you find a 0 that's sandwiched between numbers that you've already decided are significant, they too are significant. You cannot have numbers that are insignificant between significant numbers. Okay? So, here's a 1.009. The 1 significant, the 9 significant because of rule number 1, and the 2 zeros inside got sandwiched, and they therefore are also significant. Got it? Not so bad. What about these zeros? Okay? You just gave me some zeros like this. Here's a 0 that's been placed in after a decimal point. One would presume that somebody did that on purpose, otherwise they would just say 4. What's the extra 0 mean? It means that the precision of the device was such that we could actually tell one more decimal place, and it's still on the 4, as best we can tell. So that means something. What about that 0 there? What if it's written in scientific notation? In all 3 cases, if you're looking and you find a decimal place and a bunch of numbers and zeros on the end, those zeros are significant. We call those final zeros after a decimal place. They have to be after a decimal. Okay, so far I've got 3 things that make zeros significant. No, 2. Sandwiched and final zeros after a decimal. So far so good here? Well, you got to know that there's going to be some times when zeros are not significant then. Because everything's been significant so far. Right? Okay, if a 0 is just holding down a decimal spot, it's not significant. I don't mean to say that it's not important. I mean in the definition of the word that we just used for significant, it's not significant. It does not fulfill the role of a scientific number that is significant. So the 0 doesn't count, but the 9 and the 8 and the 4 would. The 0 doesn't count, but the 6 does. Okay? Now watch this. If you start a decimal point, and you start seeing zeros come after it, those zeros are still not significant until you run into a number that is not a 0. Okay? So if you have a string of zeros, 0.004, you don't get to a significant number until you finally get to something that's not a 0. 1 significant figure. This one, by the way, in our work over the diagnostic test was the one that people seem to have the most trouble remembering. I kept saying that this one had 3 or 4 in it. Okay? So that one has 1. Seems like we just already covered that, right? Is that a repeat? Yeah, it's the same thing. Okay. Finally, the weird case of a number that has no written decimal point, and yet there are zeros before the decimal point. This is the hard one to figure out sometimes. These 3 zeros are not significant the way it's written. If they're just place-holding zeros and there's no written decimal place, we count the non-zero. The 7, we don't count the zeros. How about this one? Oh, what about that 0? Not significant. Now, I asked you on either your homework or your diagnostic how this could be fixed. And everybody wanted to put a decimal place in here. Okay? Now, that would fix, quote unquote, fix the fact that we could make all the zeros significant. But the way that would have to be done so that would actually make sense in an experiment would be we would need a device that actually measured to that place. It was precise enough to give us that answer. And we can't just make numbers significant if the device really wasn't that precise. Okay? So you can't just slap it down there if you want to. Okay, so these are the rules of how you detect whether there are a certain number of significant figures. There are 2 exceptions to the rules about how many sig figs are in a certain number. One is items that were defined to be equal to each other. Okay? How many seconds are there in a minute? 60. Is that a measurement where you actually timed it and you're sort of off? It could be off by as much as a half of a second. No, they're defined as each other. We invented that definition. So when we multiply by that later on, we're not going to have to worry about whether or not that's going to affect our precision. How many meters are in a kilometer? Well, we decided that the prefix kilo means 1,000. So if there are 1,000 meters in a kilometer, it's exactly 1,000 meters, not sort of estimated 1,000 meters. Do we understand each other? So when we have definitions, we don't have to worry about significant figures. I guess the best way to say it is it's infinite sig figs are infinitely right with no error whatsoever. Finally, numbers that are counted. I mean, literally, when you do something like this, and I hold this up and I say, how many pens am I holding? And you say 2, and I will say, give or take how many? Give or take 1/2 of a pen? And you go, no, that's ridiculous. I can count them. I can see there are 2 exactly, and I give or take 1/10, and I give or take 1/2. Exactly 2. Okay, exactly 2 means no uncertainty or estimate. So if the number of items was counted, then we'll say, for sure, that's just like a defined number. It has infinite sig figs. No error built in. Okay? All right, so you put all those things together. You can look at a number and diagnose how many significant figures it has. Okay, now the next thing you have to do, and where some of us struggle, is how do you take significant figures and then do math with numbers that have sig figs in them? All right? And a moment ago, I just gave the example of adding the amount of money the 2 of you had together when we didn't know for certain how much you had. Well, whenever we do math with numbers that have estimates in them, and we combine them together in calculations, the combined estimates have to be carefully dealt with. Okay? And so in general, we say this. If you calculate an answer, the answer that comes out can't come out to be more precise than the terms that you used to get it in the first place. Why does that make total sense? If I know how much you have within about $5, and I know what she has within about $5, and then I'm trying to figure out together how much money you have, how precisely can I know the combined amount of money that you have? Well, I certainly can't tell you down to the penny, can I? You see, I can't be more precise than the uncertainty that I had in the first place. And now I'm combining uncertainties together. So this is the principle that drives the rules. Now, how is that going to show up? If you make an error in calculation and you have something like a 5.0 times a 2.0, what is it saying? This has 2 sig figs, this has 2 sig figs. You multiply it out. What happens if you say 10? That's only got 1, right? So you gave the impression here that you lost some of your certainty just by doing math. Well, that's not right. Nor could you gain it and say, I know down to, here. Now, if they're not zeros on your calculator and you write every little decimal that shows up on your calculator, you've done the wrong thing. You've disregarded the significant figure process. And you'll see me write that on your paper. You disregarded the significant figure rules. You just wrote everything that showed up on your calculator. Okay, so it's time for us to figure out what to do. Okay, so you cannot create precision just by doing math, by adding things together. So your calculated value then has to be rounded off to make it consistent with the precision of the measurements that it came from. This makes sense. Okay. Here are the rules then. It comes down to a set of rules. Let's talk about rules for rounding first. Rounding a number. In this class, to round a number, you have to first decide how many significant figures this answer has to have. I'll show you how to do that in a minute. Okay? But this decision depends on the given measurements that you have and on the process that you use to arrive at the answer. We're going to get to that in a minute, but let's see at least how you round a number in this class. Okay. I saw this on a test that was given earlier in the week. All right? This is the speed of light in a vacuum as it races through space from the sun to us. Could you write that? How many significant figures does this number have? We don't know by just looking? 3. The 2, the 9, the 9. Does the power of 10 affect it? No. Okay. Could you write it with only 2 sig figs? What would you have to do? You start from the left, count 2, 1, 2. No, you have to stop right there. But you're going to have to get rid of that last 9. And does the getting rid of the 9 actually do anything to your reported number? Can you just chop it off and leave 2.9? Or do you have to do something? You do have to round. Okay, so you just told me that once you know how many significant figures your answer has to have, we just said 2, you're going to round to that many digits, counting from the left. 1, 2, we're going to stop right there. Okay, and I have to figure out how to round there. If the digit immediately to the right of your last number now is less than 5, you leave that number alone. But if it's 5 or greater, what are you going to do? Round up means what in this case? This would have to go up to a 10, which would push this one up to a 3. So that would be 3.0 times 10 to the 8. Do you understand? Okay? These are things, guys, that you have done throughout high school. This is pretty much a senior level class. So that's the expectation that everybody knows how to do that. And if you don't, you brushed up on it. So that you can do it by next Tuesday's test. So if it's 5 or greater, we're going up. And if it's under 5, we'll keep it down. So, can you give that one to me in 4 significant figures, please? 314.721. I want 4 sig figs, please. Say it loud. I'm sorry, that's just my bullets going down. 314.721. 314.7. You did not say 8 because? Because 2 is not big enough. All right? 314.7. I want 2 out of that one. So coming from the left, you need to tell me where the first significant figure is. You're using the rules we just went over. Where's the first significant figure? Is it here? No. They don't count until you get there. There's the second one. They want us to stop at 2. So we need to stop at this place. 0.00. Could you write it in scientific notation? If not, you need to come tomorrow. We're doing that tomorrow. Okay? All right. 0.0018 is correct. How about this one? 2 sig figs, please. Now this one's tougher. Come from the left. 1, 2. I want to stop right here. Look to the right. I know I'm supposed to round up. Do I just say 88? This number is 8,792. I can't just make it an 88. What should I do? I need two significant figures, and I need place-holding zeros that are not significant to hold the spot. So I'm going to pull this up to an 8 and replace those two with zeros. Non-significant zeros with no decimal place, correct? Could I write that in scientific notation? 8,800. Okay, every one of these numbers we have to be able to turn into scientific notation and back again. So that's 8,800 meters. You've seen 3 examples with decimals on both sides. You need to practice those things before Tuesday. Now, here are the rules you seem to know or not know. And this is the one you seem not to know as much. And when I'm running out of time here, I want to hit this one first, because this is the one everybody seems to mess up. There's one rule for adding and subtracting with significant figures, and there's one rule for multiplying and dividing. Since most of you came from chemistry, you remember the multiplication and division one very well because you did so much dimensional analysis all the time. You were multiplying all the time. Okay, so you got that rule down pat, but you can't use that rule when you're adding and subtracting. Okay? So, the little rule about go with the fewest number of sig figs, you know what I'm talking about? For multiplying, only works for multiplying and dividing. Let me show you what we do with adding. Okay, I want to add these 3 numbers up. Okay, so I'm going to add. They're in meters, so they're obviously measurements. The first thing you do is you stack them up on top of each other like you were in grade school, like this, so that the decimal points are on top of each other. This is really important. And then you start looking at columns. Hundreds columns, tens columns, 1 column, 10th column. You walk across your answer until all of a sudden one of your terms runs out of decimals. This one ran out first. Do you agree? There's nothing there. Consequently, my answer can't have anything here. So what I do now is I mark a column. I've marked the last column that had digits for all of them in it down here. Now watch, if you punch this into your calculator, you get 369.76. But on your paper, you're supposed to stop here. You've already marked the column. You figured that out. What do you do with that 7? You leave it alone? You have to round it up. And the only way to know that you would round it up is to actually add it all like you were in math class and then look 1 column to the right. This is what you must do for addition and subtraction. For multiplication and division, I think you're more familiar with it. We didn't get that far. I have recorded this session and I have this presentation already posted up to It's Learning. If you want to go look at this at a more leisurely pace and make sure that you know it, I'm going to come in next Tuesday guns blazing on this stuff. It's old news. We should know it. We've been in high school 3 years. This is the review of that. You guys get ready. If you need to talk to me about it later, come on up. Make sure you signed in for me. I need to know that you were here.